Friends, welcome to this course on robotics. I will be giving the introduction. This is the first lecture in this course, and in this lecture I will give you an overview of what the area of robotics is, and in the subsequent parts of the course we will go through the more details of this particular area. So, let me begin without much preliminaries, directly go into this subject of robotics by giving you details, beginning with what we call as automation. Automation, there are two types of automation. One is hard automation. This has been there for a long time. Most of you are familiar with it, both at home and in the industry or elsewhere at work. Familiar examples are sewing machines, washing machines, electric irons. These are all forms of automation. These are what are known as hard automation, many of these forms, in the sense that you cannot do much of a change over from one particular type of work that the automatic machine does to another type of work that you desire. It cannot handle product design variations. This sort of automation on the shop floor, if there are changes in the design of the product, this sort of automation cannot handle. But it has served us well for several years. For example, you have these automatic devices in a lathe, you have these in a shaper, all this has served us very well. Subsequently, people came out with what is known as adjustable automation. You want to adjust the stitch length in your sewing machine, there are some adjustments which are provided, and you could adjust the stitch length. Similarly, you could adjust the pitch of the screw you are turning on your lathe, and so on. These are what are known as adjustable devices, which have been used after when once people sought a variety of products, but of the same nature. Subsequently came what is known as programmable automation, though it is not very clear as to when this emerged. This began particularly with the arrival of computers, when people started reprogramming machines to do a variety of tasks. And then we have come to the highest level today, what we call as autonomous devices. This is robots belong to this class of autonomous devices, and are perhaps a very good example of what can be achieved if we combine the power of the microprocessor with conventional automation systems and arrive at very powerful systems. The number of systems which are available to you in this class today are enormous. It is very difficult to describe or list down what are the various systems which fall into this class of highly programmable and autonomous systems. These autonomous systems are endowed with decision making capability, and that is a very important thing. You would like the machine itself to take a decision rather than human being continuously interfering and resetting or changing whatever it is. If there is a fault, the machine itself detects and corrects itself. So, we have slowly reached this high level of automation, and we are tending towards living beings. Animals have certain degree of autonomy. When they move around, they see food, they move towards it, they sense the presence of food or a threat through several ways, through sight, through smell, and so on. And they react to the environment and do what they desire or what is best for them at the given moment. Perhaps among the most autonomous devices or autonomous capabilities are possessed by human beings. They are the most advanced in terms of autonomous capabilities. We think and we react, and we can change our actions, we can plan new actions. This is the highest level of autonomy which most of us encounter. Now, where does the robot fall into this? Many people seem to think that robots are like human beings. It is not really so. We can develop machines which can be autonomous like humans and machines, but do not reach the same level of autonomy. This is because there has been tremendous development in digital electronics and a lot of development in sensors. All these put together, the marriage of these devices together, have made it possible for us to now come out with autonomous devices which are many a time called robots. there is no definite this definition of robots. I shall now show you a short clip to indicate to you how much of what you call that how much is possible, autonomy is possible when we have a marriage between electronic systems and mechanical systems. Let us have a view look at this particular clip. Here is a two-wheel machine which is balancing itself. This has been built by an IIT student, and this particular machine has been using gyroscopes in order to balance itself. What is the utility of such systems? Such autonomous systems can be used to undertake hazardous tasks. Painting on the shop floor is a very hazardous task, because you are handling toxic material and it is injurious to the health of workers. Welding is a hazardous task, and also welding is a difficult task. The human being, if he has to weld two pipes together sitting on one side, he has to weld all round the pipe, whereas he is able to see only one side of the pipe. Then loading and unloading jobs from a press or from a lathe is a tedious repetitive task. This is one more place where robots come in and can handle them with ease. Assembly operations. For example, when you assemble a chip, you have a very fine wafer, silicon wafer, to which you have to solder very fine wires. Lot of precision is required. It is not so easy to do, because human beings cannot handle such very precise tasks, and that is where the robots come. Such tasks, when handled by robots, promise consistent quality. That is a very important reason why robots are being increasingly used. Second thing is, you could reprogram the robot if there is any change in the design of the product. For example, if you are welding or if you are soldering 50 leads in a chip, and then the next chip requires say maybe 32 only, then the robot can be reprogrammed to solder 32. Yet another reason for use of robots is safety. When they are handling dangerous material, chemicals, biochemicals and nuclear material, safety is paramount, and robots can handle this material with ease, with smooth operations and repetitively without fatigue, and so safety is promoted. I have already spoken to you about handling of fragile and miniature parts, fragile parts like vials of medicine. These require careful handling, and that is one more place where robots come into the picture and can do the task with much ease. Further, you must have all heard of exploration of planets like Mars and all other like the moon. Here we need devices to move around, gather samples, do tests and so on. When you want to operate in such remote areas, it is very easy to use robots and undertake the task. Even for terrestrial applications, there has been recently use of robots for exploring volcanoes, for exploring remote heights in inaccessible places in mountain ranges. All this has been done by robots, or underneath the sea. That is another place where you are all familiar with the Titanic and how the wreckage of the Titanic was surveyed by an underwater robot. Okay. Now, we have seen all these things. Let us now go over to a few of these, whatever I have mentioned, the tasks I have mentioned. Here I show you a picture of a robot painting a car. The car is sitting on the conveyor. The car does not stop for the robot to paint it. The conveyor moves at a very slow speed and the robot keeps painting it. You get a uniform coat on all the cars on the conveyor, because the robot has been properly programmed. It repeats the same thing over and over again infinitely. Okay. So, that is one of the reasons why robots are used, in order to get uniform quality and good quality. Let us see a picture of a painting robot. You can see the painting robot painting a car here. Notice that these painting robots have a high degree of flexibility, in the sense that they can maneuver inside through the window of the car they can maneuver in and paint the ceiling of the or the roof of the interior of the car. These things can be done, these robots can do it with ease. A man, if he is supposed to, a worker who is required to do this, will have to carry a heavy painting gun, will have to mask himself to keep the toxic gases out of his breath, and there is always the hazard that there would be a fire. Now, painting robots are special in the sense that they should be able to ensure that no fire breaks out when they are acting. What is the status today of these robots? There are what are known as industrial robots. That is the one like the painting robot you see. There are robots similarly in industry which unload and unload what are known as presses. These are very hazardous tasks. In a press, when a sheet of metal is introduced, there have been many accidents where the workers' fingers have been injured by the moving ram of the press, which sometimes comes in, and the worker forgets to remove his fingers in time from the loading point and gets them crushed. There are medical robots which help a surgeon undertake intricate surgery. There are mobile robots which allow you to go and survey various planets, remote areas in nuclear power plants or in chemical power plants, inaccessible areas. These could be wheeled or legged. Wheeled robots can go wherever there is a smooth surface or an incline, but also on off the road terrain. A legged robot on the other hand can step over obstacles. Wherever a human can go, the legged robot can go. There are many places. All you have to do is imagine that wherever a horse or a goat or a human can go, a legged robot can theoretically go, where people are still trying to build devices which will approach that level of confidence and performance. People have also started, many scientists have begun coming out with what are known as hopping and running robots. Then there are robotic aircraft. You must have read about these, where these aircraft without any pilots go and survey the enemy territory and guide the land armies towards the enemy's fortifications. These have also been used in rescue operations to spot people who are trapped during earthquakes and other places. These robots have been used. These are all autonomous. They keep flying around, and when they using cameras on board, people can direct the robot towards the robotic aircraft towards the target. There are also robotic boats, submarines. Of course, robotic toys are there. They have become very popular. You find them almost in every shop now. And there are also robots for entertainment, little robots. We will show you one as we go along, which are companions to the elderly and entertain them. One of the most important tasks at home and in industry is cleaning. There are robots for cleaning. This is just an example of a few applications of robots. If you were to really ask me, I would say there are much more number of applications possible today through this marriage of mechanical engineering, electronics, computer sciences, artificial intelligence, sensors. I mean, it is a multi-dimensional area involving almost all aspects of engineering. If you want to look at smell, some aspects of chemical engineering come in, and there is no end. It is a very big area which draws in upon the scientific expertise in almost every known technology, technology known to humans. So, we will begin with industrial robots. I show you here a simple industrial robot built in our laboratory here. It is known as a SCARA robot. It is a very simple device. We had built it. This is one of the earliest ones we had built. It has been built out of stepper motors, something which most of you are familiar with, and is controlled by a microprocessor which is to the right. It could conduct and replicate simple tasks repeatedly. There were three motions. The main motion is the motion of the base around a vertical axis. Second, there is a sort of an elbow motion, and third, there is an up and down motion of the gripper as it moves up and down. These three motions we had put together using a set of links, a set of drives, stepper motor drives, and also a rack and pinion system for the up and down motion. We control these stepper motors using the microprocessor, and in between the microprocessor and the robot you have the drivers for the stepper motor, and through such an artifice we could control the robot to do a variety of tasks. Here is another robot we had in our laboratory. This is driven by servo motors as opposed to stepper motors. So, obviously, if you want to know, in a stepper motor you give the number of steps, you know how much the motor has rotated. In a servo motor the same thing is done by having what is known as a feedback. There are encoders here which provide you the feedback, and as you notice the motors convey their motion to the various joints through a set of chains. As we go on, we will see how this particular device works. I will now show you a short clip on this particular device. Let me just show you how this device can be used to transfer the contents of one glass into another. Now, it is a clip which runs on for about 1.5 minutes. You can see the robot, you see the motions, the various motions. The robot has got 2 fingers. You see the robot has approached you have got a glass there containing orange juice. The robot is picking it up by the stem. It is now lifting it up. It is turning around towards us. You watch it, it will turn. It is stretching its arm, goes to that position, then turns, and then it is emptying this orange juice into another cup very slowly. It does not want to spill, and you see there it has completed emptying the orange juice into another cup. Now, it is returning the stem glass to its original place. So, we will now see, apart from these robots, we have got what are known as mobile robots. I show you here the picture of one mobile robot, which is a tracked vehicle which can explore uneven terrain. As you can see a couple of motors driving through chains, the tracks. Here is another view, you can see the battery. All robots more or less are required to carry their power on board. Okay. They are not connected through wires to a land source of power in the laboratory or in the industry. Mobile robots invariably have to carry their source of power on themselves. Robots which are stationary, like the Rhino I had shown you, they could be powered by from a stationary power source, but mobile robots. So, whenever one designs these mobile robots, the ability to carry a lot of power in a compact package becomes a limiting factor. Here is another little robot which can follow a line on the ground. This has been built by one of the companies established by our students. This robot can follow a line which is drawn on the ground. You have a white line on the ground and this robot follows it. Whichever way it is, you can draw a shape figure of 8 and the robot would follow. How does it do it? It does it through a set of sensors which allow it to sense the position of the line and guide the robot accordingly. Here is what is known as a walking device. Earlier I had told you that walking robots can cross over obstacles, can cross debris wherever there has been an accident, something which a wheeled robot cannot do. Tracked vehicles can do, but supposing a tracked vehicle is asked to step over a pipe which is at a height of maybe 2 feet from the ground, without damaging the pipe, a tracked vehicle will not be able to do it. It will damage the pipe, whereas a walking device can step over the pipe and walk off, just like a human being does. Without damaging a pipe, I can cross a pipe. Here is one. This is one of the earliest walking machines built in our laboratory here, and it has what are known as single degree of freedom legs. You can see the leg, it is a mechanism. What the leg essentially does is, this mechanism does is, it permits the leg to lift itself up, throw itself forward and come down. So, it was a single degree of freedom leg. This had a limited capabilities. There were 6 legs in the machine, as you could see here, 3 legs on this side, 3 legs on the other side, and it had a limited capability because it had single degree of freedom legs. The legs were driven by stepper motors, so we could control. When one leg is moving in the air, another leg is stationary. Watch how you walk, you will notice that when you lift and throw one of your legs forward, the other leg is stationary. In the case of these 6-leg robots, here we have 3 legs stationary at a time on the ground to provide a tripod support, and 3 other legs are thrown forward, thereby we achieve stability. Another robot where we have a leg with 2 degrees of freedom, a little bit of more freedom than the previous leg. You notice this robot also has got 6 legs. Again we are aiming at static stability in order to keep it stable. There are 6 legs. You can see the black boxes there. These are the servo motors which drive individual legs. Each leg has 2 degrees of freedom. So, 2 servo motors are required to drive the leg. Now, what do I mean by 2 degrees of freedom? Look at yourself. You can move your shoulder and your elbow. You can move this up and down and your elbow up and down. You need one motor here, you need one motor here. Similarly, when you lift your leg, you need a hip joint, and you also need a motor at the hip joint, and you also need a motor at the knee joint. So, this particular robot has got something similar. Okay. Now, we will see. This robot is shown carrying a camera on the front to go around and survey places where there has been a little damage. We use this as a laboratory robot for our experiments, and it did work successfully. It could see and locate objects with the camera and move towards them. Here is a very sophisticated 4-legged robot. This is the Aibo built by Sony Corporation. In its nose, it has got an infrared sensor which can detect the orange ball out there. Then it has got a sound sensors which can receive sounds, and it can determine from which direction the sound is coming. It has many other sensors built into the system in order to enable it to behave almost like a real puppy. This picture shows the Aibo playing football. The orange colored ball is colored orange in order to identify the ball to the Aibo dog. It is a very popular one, and it is now being used as an entertainment pet by senior citizens. We now come to one more robot which has been built here at IIT Bombay, the 6-legged robot called Natraj. This has 6 legs. Unlike the previous robots which also had 6 legs, these 6 legs are disposed around a circle, as you notice here. You see, there are 6 legs. So, we have them disposed around a circle, and you can notice that there are red colored units on the robot. These are the actuators which actuate individual legs. Each leg has 3 motors, and a total of 18 legs are there. As you can see here, the red colored, these are the motors. Each leg has 3 motors, so 6 legs makes it 18 motors. In the central portion is the electronics in the central well. There is also a 486 computer sitting in the central portion, which synchronizes the motion of all these 18 motors in order to arrive at a particular way of walking. That is what we have done with our Natraj robot. I will now show you a clip of the Natraj robot. You will now watch the robot walking forward and backwards. As it walks forward and backwards, here you will see, here is the robot. You can see the size of the robot in comparison to the humans around them. You can have a look. You can see the motors, the red and green ones are the motors, then there are ball screws which are used, and then we have all these. Now you can watch the walk. You can very clearly see the robot lifting up 3 legs, throwing them forward, okay, in order to move. The front 2 and the rear 1 leg, it is moving. It is a very slow motion because the robot is very heavy. This was the first walk it took. I am showing you the video of the very first walk the robot had taken. It has taken about 2 steps, it is taking a third. You can see the lights from the electronics, the LEDs on the central electronics in the central well, which are controlling all the motors, all the 18 motors simultaneously. Notice that it is now walking backwards. So, this robot can climb because it has 3 degree of freedom legs, it can lift the leg up and climb any object. Now that we have seen all these types of robots, let us just summarize what we have seen. When we extrapolate from nature, we find that there is an equivalence between humans and animals, and we are trying to imitate these human and animal, what you call that, their abilities. That is what we are trying to imitate, the abilities of the humans and animals. For example, we have arms and fingers to manipulate objects, robots have a similar capabilities. We have legs for locomotion, robots have similar capabilities, and actuators are muscles. In our case, we have electric actuators, there have been hydraulic actuators and pneumatic actuators in robot. Our eyes provide us vision, and we have cameras mounted on these robots. I showed you one little walking robot with a camera, which allows it to see various objects around it. We have, of course, many more additional sensors, like the ability to sense smell. Scientists are trying to develop equivalents for this, which could be used in robots. We can hear, robots can hear using microphones, convert the sound into something useful. We have a tongue in order to taste food or whatever it is. One day, scientists hope they could come out with robots for a similar purpose, and we have some very surprising sensors like the skin, which can sense temperature, which can sense touch, a tactile sensing. People are attempting to come out with sensors of similar nature for robots, and we have nerves for communicating with the brain. There are electronic devices for communicating with the computer in a robot. So, when you look at nature, we are trying to mimic nature through robotics, and many a time, in order to understand robotics, it suffices if you understand the corresponding nature. Whenever I try to explain to students how an arm works, arm like the one I had shown you, transferring orange juice from one glass to another, I usually use my hand as an example and tell them that, look, if I were to command you to rotate your shoulder or your elbow by this much, 90 degrees, you would respond, and the muscles would have actuators and they would fold the elbow. In a similar fashion, in a robot also we need these. We need the muscles in the form of motors. We need something which could hear our command, convert it into a command to the motors and move the motors to the necessary angle. So, we can always use the analogy of a human being or an animal in order to explain many of the things that these robots could do. Though we do them more easily, we do not realize how complex it is to convert our performance into, or to make a machine which would mimic our performance is quite a complex task. Now, here I show you something which mimics fish, a submarine which goes underwater. This was built by one of our students. There is a small propeller which is not shown here, and it has some electronics which allows it to sense the quality of water in a pipe or in a tank, both on the surface and below the surface, and transmit this data to a land station. This is what we have built. Here is a photo of a medical robot. Any surgeon, if he wants to operate, he cuts open the body and then operates. This is always a dangerous thing because many bacteria get in and infection sets in. Now, what they do is they make a simple keyhole, and through the keyhole they send a little device in order to cut or suture or suck blood or whatever device is used for doing an operation. The devices are made tiny and they are sent in through a tube. You can see 3 tubes being sent into the body in this particular picture. One tube carries a camera so that the surgeon can visualize what is going on, and then he guides the little robot which is passing through another tube and guides it and commands it to do the task which he thinks it ought to do. Okay. Here are examples So, having seen the various types of robots, let us look at some of the robotic components. Here are the 3 motors which we had used in our Natraj. We had converted conventional motors into servo motors. You do get ready-made servo motors also. In these motors, you have a feedback. Let us assume that the motor rotates through about 20 degrees. How do you know whether it has rotated through 20 degrees? Obviously, a potentiometer will allow you to determine how much the rotation has been. You can always measure the voltage output of the potentiometer and determine. Such devices are incorporated into servo motors, and together with the assistance of the 2 electronic boards which are shown, one can command the servo motor to rotate through the given angles, so on. So, here are examples of servo motors. You will be seeing this as you go along in the course. Here is the leg of the robot. You can see the 3 motors, the Natraj robot which we had built. You can see the 3 motors clearly, they were reddish looking ones. These 3 motors are the servo motors I had mentioned in the earlier slide, I had shown you in the earlier slide, and these 3 serve to move the foot up, down, or to the side, left or to the right, or to the front or to the back. This is what these 3 motors are out. So, you see you have a up and down motion which is provided by one of these 3 motors, a forward and backward motion provided by a second motor, and an ability to look to the left or to the right provided by a third motor. Okay. Now, these 3 motors, we had designed a special mechanism, as you can see, there is a mechanism for the leg. This mechanism allowed us to decouple these motions to a certain extent, if not fully, and by commanding these 3 motors, we could get a variety of motions for the tip of the foot of Natraj. So, here is an example of execution of this, all that we know in robotics, into something like this. Now, the leg and the rhino or the other robot I had shown you earlier are somewhat similar. They have the same, what you call, if you watch your own leg and your hand, you compare them, the shoulder is equivalent to the hip and the elbow is equivalent to the knee. So, if you know how to design a robotic hand which will transfer objects from place to place, you also know how to design a leg for a walking robot. Let me just show you a movie of the walking robot, the Natraj robot. I will be showing you a movie of the Natraj robot now. The Natraj robot was built at IIT Bombay, as I had said. Here you can see it is a massive robot. You can see the various motors, and I am just repeating this in order to show you, give you an appreciation of the size of the robot, as well as you can see this. So, we have seen these robots, how they are, whether they are an arm, a robotic arm or a robotic leg, they are equivalent. Now, let us see how is one going to tell the robot what it is supposed to do. For the painting robot, one traditionally does it by what is known as teaching by showing, teaching by walkthrough, that is what we call it. Whenever you have a child, when you want the child to write the alphabet, what you tend to do is you hold the child's hand and make him write the letter A or B or whatever it is. The child is holding the chalk, you hold the child's hand and lead it through the paces. So, this is called as lead through teaching. Now, this is typically used in painting. As you notice, a worker is handling the robot, he paints the car with this. The motion at the individual joints of the robot, you have seen that as the robot moves, there are motions at the individual joints, these are recorded, and when one replays them, you get the robot performing the same task flawlessly and repeatedly. If the worker has painted it badly, the robot, obviously the result would be a bad job of painting, but very skilled workers are used for this task. They do an excellent job, and the entire motion of the various joints is recorded and replayed, and whenever a car comes on the conveyor, the robot automatically replays the program that it has been, replace the particular program which has been stored, and painting is flawless. So, let us now go on to the next. Here is another way of teaching a robot, showing it what is the task to be done. The entire robot and its environment is replicated as a virtual world on a computer, and the robot is put through its paces in this virtual world. all the motion parameters, all the parameters associated with control of the robot are captured, taken down to the shop floor, and the disk is fed to the robot on the shop floor, and the robot on the shop floor faithfully reproduces what has been programmed in the virtual world. The virtual world contains all the machines sitting close to the robot, all the loading stations, all the components. So, without much of wastage of shop floor time, these robots are programmed. Compare robots with nature. Manipulation, arms and fingers driven by motors and other form of actuation. For vision, we have cameras. For hearing, we have microphones. For smell, they are yet to develop. For taste, they are developing. For feel, what are known as tactile sensors. For communication, we have wires, fiber optics and radio systems, and for brains, computers and microprocessors. This is what we have in robots as compared to nature. Robots need not be so advanced. There are very simple devices which can be used where you have hazardous tasks to be conducted. Here I show you one such simple device. This is a device to climb up a pipe. Here you have got one bellow in the center and two balloons at each end. Now, let us assume this is pushed into a pipe and the balloon on the extreme left is inflated. It is pushed into a vertical pipe with the balloon on the extreme left inserted into the vertical pipe. When the balloon inflates, the whole thing hangs there because the top balloon is holding on to the side of the walls. Then you push it further and inflate the bottom balloon will hold on and deflate the top balloon. Once you do this, you inflate the intermediate bellow so as to push the top balloon up. Though it is deflated, you can push it up very easily. Once the top balloon has reached a particular position, you inflate it and grip the side of the tube with it, then deflate the bottom balloon so that it does not touch the wall of the tube, and deflate the what you call the bellows. The bottom balloon rises and goes up. Then you repeat the cycle again by inflating the bottom balloon, deflating the top balloon, inflating the bellows. You repeat the entire cycle. This is how these simple devices can be used. We had done this device and used it to climb up a pipe. It can go through curved pipes also. So, we have seen, friends, a lot about various robots, starting from very advanced ones. We have also seen that it is possible to come out with very simple devices for robots. Now, I shall close this lecture. In the subsequent lectures, you will learn more details about what are known as industrial robots and industrial manipulators. But before I do that, I will show you what is an example of autonomous capability. In this particular clip, you will see an autonomous robot solving a maze. It is going through the maze. You can see that. This has been built by one of our IIT Bombay students. Wherever there is a gap, it senses the gap and moves. You can see how it has gone from the edge of the maze to the center. I will replay it again. You can see this robot. Whenever it senses a gap, it moves. You see the speed at which it turns. All this requires a very careful attention to mechanical engineering, dynamics, servo motor control, and artificial intelligence. He uses artificial intelligence to know where exactly the robot is going, and he captures the motions of the robot, the turns it has made, memorizes them so that the next time around it does not make the same mistake. It maps the maze and solves the maze second time around at a very high speed. Such robots could be used to explore mines where you have no reference points in order to know where you are going. You can move around randomly first and find out and determine a map of the mine, use it to come back. So, such are the capabilities. Here, this particular example which I show you is typically the capability of computer science and artificial intelligence married to mechanical engineering, the dynamics, because if you want to turn so fast, you have to really work out the dynamics properly, otherwise it will keep spinning on the spot. Then electronics, you have to sense where the walls are. If there is ambient light changes, the sensors will not show you the exact location of the walls, because it may show you the wall across the gap rather than the fact that there is a gap here, all these factors. So, here is an example of several disciplines coming together into a successful product, robotic product and an autonomous robot. I think we will in the next class look at industrial robots. With this, I conclude my lecture and thank you for your attention.